Next, we will have Michael Obrist. Sorry, I can't pronounce correctly your surname, from PSI. So please, Michael, go ahead.
Yes, thank you. Hello, everyone. I hope you can see my screen.
Yes, perfectly.
Okay, perfect. So my talk will be about my cement model that I have created, and the presentation I prepared for today is pretty much based on the methodology, how I connected the energy flows to material flows and all the production process steps. And it will show what are the advantages to create such a model. But before we start, I would like to introduce myself. My name is Michel Obrist, and I'm a PhD student here at PSI in Switzerland in the Energy Economics group. So as a starting point, I just want to clarify what kind of model that I'm talking about in my presentation. So we have basically a time-spaced demand model of the cement industry subsector. So it covers the cement sector in Switzerland, and we have used this model for our analysis until 2050. But because it's kind of a decoupled model from the energy sector, we also needed some exogenous inputs. For example, we took prices of the energy carrier from our national energy system model that we have developed here at PSI, which is STEM. And what we also have defined exogenously was the cement demand based on production forecasts. And we also defined that the policy with a scenario analysis, so policies targeting an energy efficiency target, or policies applying a CO2 tax or a CO2 cap. And of course, now it's what I'm talking about today is the decoupled model that we have created, but the plan in the future is then to connect this subsectoral model to the national energy system model. So when I'm talking about connecting material flows and production processes to energy flows, I want to clarify what I mean by that. So what we have done so far in the model usually, or in the models usually, is we have on the right-hand side, we have our energy service demand, as we all know them. For example, could be process heat or mechanical drives. And we have the input into the demand module, which are the energy commodities. And what connects those two is basically then our model. And we changed this basic methodology a bit. So on the right-hand side, what we have as a demand now is not the energy service demand, but it's a product demand. In the case of the cement model, it's the cement demand. Then we have some semi-finished products in the model, and some base products to start with. And what the model now does, we model each production step. For example, the conversion from raw limestone into hot clinker, which is a production step for producing cement. And for that, we then need again our energy commodities. And we also produce some byproducts. In this case, would be process-related CO2 emissions or energy-related CO2 emissions. This is just to give you an overview about the general modeling technique that I have applied in my model. And why are we even doing this? So with this new modeling technique, we can specifically account for efficiency improvements that we have in single process steps. For example, that could be some mills with higher efficiencies or some kilns with better insulation. But then we can also account for improvements that are related to the production process. So for example, if we can recover waste heat from one production step and reuse it in another production step, that could be a process-related improvement. But we can also account for material and efficiency enhancement. So cement basically or the main component in cement is clinker, but the clinker can also be substituted by what is so-called supplementary cementitious material. Those materials are often waste products from other industries, and they can replace the clinker in cement without decreasing the properties of the cement too much. And this gives the advantage because the clinker is by far the most energy intensive product here. So we can then decrease the energy intensity of the cement. What we can also account for directly are, for example, process-related emissions that occur from the chemical conversion of limestone into clinker, and we can account for that exactly where it happens. This is an important point if we want to apply CO2 capture. So this is the full scope of my model. I would like to go through some of the features here. So first of all, let's start with the basic production path of cement. So what we have included are the usual steps that you need to produce cement, starting with raw material mining over milling to homogenization, and then we go to the pre-calciner and the kiln. This is the most energy intensive, or those two steps are the most energy intensive processes here, or where we consume basically all the process heat that we need. Then we have a clinker cooler, where the clinker cooler, once it is burned, it's cooled down. Again, mill, packaging, and then it would go to the concrete plant, which is then out of the scope of our model, and go to the building stock or the infrastructure. So the next thing I would like to highlight is then the opportunities that we have for process-related improvements, as I mentioned, for waste heat recovery. So waste heat can be recovered from basically three process steps: the clinker cooler, the kiln, and the pre-calciner. And usually waste heat from the clinker cooler, for example, is used to preheat the combustion air that is then used in the kiln. And waste heat from the kiln is often used then again in the pre-calciner at a lower temperature. But now with this modeling technique, we also have the opportunity to do other things with the waste heat that we have available in the process. For example, we could feed it to an organic Rankine cycle, or we can just feed it into the district heating network. What is also an option is when CO2 capture is applied, it can also be used for solvent regeneration. Another feature in my model that I don't want to go in specifically is then the reuse of demolished concrete. So we can basically reuse the demolished concrete again as a supplementary cementitious material, as I mentioned before. But I don't want to go through all the process steps here today. But what I would like to explain a bit more in detail is how we modeled our burner and how we modeled the flexibility that we have with different fuels. So usually in a cement plant, the fuels that are burned is coal, mainly coal, and then you have some alternative fuels. That could be, for example, biomass. It could be also waste products like scrap tires, waste wood, or waste oil goes also to the alternative fuels. But you would also have the opportunity to use gas. So you kind of have a triangle of different fuels that you could use in a burner. In Switzerland, the conventional burners, they are located approximately here. So they use a share of approximately 45% coal, and the rest is then alternative fuels. Natural gas is only used to a very low share, mainly for startup purposes. And what we have done in our model is now we give the model the opportunity to invest in different directions. So it can substitute coal by gas. It can substitute coal by alternative fuel to a maximum degree of 90%. Or it could choose something here in between. But depending on where we are here in this triangle, the model or different investment costs, they account basically for the additional investments that you would have, for example, for the fuel supply infrastructure. And that's how we modeled the burner technologies in our model. The last thing that I want to highlight from the model methodology are the CCS technologies and why we have such a big advantage with our new process-based modeling technique. So we have different CCS technologies included in the model, and the new model methodology gives us, for example, the opportunity with MEA scrubbing or with the chilled ammonia process to count the waste or to assign waste heat, for example, for solvent regeneration. In the case of calcium looping or in the oxy-fuel process, it also gives us the opportunity to account for the waste heat that applies by those technologies. We can use it in a steam cycle, for example, but or in an organic Rankine cycle. And one additional thing is because not all of those technologies are post-combustion technologies. For example, an oxy-fuel process, there you would also change the burning kinetics. And that means you would need to replace or retrofit your kiln. And we can connect that actually to the replacement of a kiln. And just to go through some result highlights that we could achieve with this modeling technique, I want to show you some diagrams here. This is the deployment of CCS technologies in a very stringent scenario. So now in this scenario, we target a CO2 emissions reduction by 80%. And with this modeling technique, we could show which technologies would play a role then in the future, and where should we put our efforts in research into. One other thing that we could show is which kiln type would be deployed, also depending on the scenario. You can see the result here. In the BAU scenario, for example, other kiln types get selected by the model than in a CO2 cap scenario. And what you can also see here, or slightly see here, the model also retrofits old kilns, and it does this even more, for example, in a cap scenario. Furthermore, with this modeling technique, we are able to specifically count where are the energy savings per production step. That's what I would like to show here. And you can see that the highest improvement is at the kiln. This is not a big surprise, as it's also the this process step that consumes the most energy. So let's sum up my presentation. So I showed you a detailed model that we used to analyze the Swiss cement sector. And the main feature of this model is that we have used material flows and production processes connected to energy flows, as we know that from conventional models. And we used this model, and here I just summarized the main results from the paper that we published with this model. So what we could show is that the energy consumption in the cement sector decreases, as well as simultaneously the CO2 emissions, they decrease, but they decrease only to a certain degree. If you want to have a drastic reduction of the CO2 emissions, then you require CCS technologies. And we were also able to put a minimum, or to define the minimum tax that you would need to define, that CCS technologies become an option in the cement sector. This is just a very small excerpt of of our results. If you want to see all the scenario analysis of all the results, then I refer to our publication. It will be available soon. It's at the moment in the typesetting process, and it will be published in the Journal of Cleaner Production. So thank you very much for attending my talk, and I'm now open to answer any questions from your side.
So thank you very much. I have few questions in my own mind, but there is also one in the chat, so let's take that one. So the question is that what is the cost difference between CO2 capture from energy and process emissions for cement plants? How do you estimate capture cost from processes in your case?
So basically, to answer the second question first, we estimated the capture costs based on the material. We didn't account, as we do this normally, where you put an emission factor to the fuel. We have CO2 implemented as a material commodity that then gets captured. If you want to know the specific costs that we have applied, then I also refer to the paper where I show all the costs of the different technologies. Of course, it also depends on the technology.
Okay, thank you. There is also another question in the chat, but I suggest that you will respond to that. Or do you have a short comment onto the second? Can you see that? I can't quite get it, but maybe you will check that and answer then on the chat, so we will move on.